Hello, everyone. Good to see you again. Let's talk a little bit more about oscillations and waves, and let's get back to the transverse wave. Though I could graph mathematically what's going on with waves, whether it's a longitudinal wave or a transverse wave. You can graph it looking like this from the mathematical standpoint of representing it. As we said, the longitudinal wave oscillates in the same direction along the same axis as the propagation is taking place, whereas a transverse wave oscillates perpendicular to how the propagation is taking place. But from the mathematical standpoint, you can, with pencil and paper, so to speak, draw waves in order to represent what's going on mathematically, drawing something like this, a sine wave. All waves can be drawn, all periodic functions can be drawn essentially by combining simpler waves and getting the more complicated wave function that you want, at least for a huge amount of circumstances. You can really, at the very least, you can approximate things very, very well that way. That's harmonic analysis. That's the use of the Fourier Series. Some pretty phenomenal stuff there. I talk about it a bit in the notes that I write about that I have available for you in Canvas. You can look at that. The person who really made that make sense to me was Dr. Ivan Sokolnikov from his book called Advanced Calculus, published in 1939. So anything good in what I wrote pertaining to the mathematics of Fourier Series and some other things as well is largely due to him. So all respect to him in that regard. So Advanced Calculus by Ivan Sokolnikov, published in 1939. It's got great treatment of Fourier Series there. You don't have to know it perfectly, but if you ever did look at it, I think you'd get a real gut feeling for what's going on. He uses a minimization process. He says, okay, well, what is the best combination of functions that would work, generally speaking, to be able to mimic any kind of periodic function? And so then he uses calculus, takes a derivative, takes derivatives and finds where the minimum would be, and from there determines what the coefficients would be for the Fourier series that would be in front of sines and cosine functions that are pretty simple to look at. In the big picture, looking at it, it's a little intimidating, but it's not too bad. He explains it just beautifully. So anything that might make sense on what I wrote for you guys, and if you want to look at it on Canvas, anything that might make sense there, very, very large portion of the credit, if not all of it, would have to go to Dr. Sokolnikov for the work that he had done way back then. He and Dr. Redheffer, Sokolnikov and Redheffer, wrote another book about engineering and physics, 1960s, also just excellent, and a lot of great stuff there. So periodically you hear me talking about that. So anyway, some excellent material out there. We don't need to know it for what we're doing as far as like being able to prove all that stuff, but if you ever run across that stuff, want to look at it a little bit, it's there for you. And like I said, probably getting directly to those books themselves are excellent. They know a tremendous amount, more than I know. So anyway, there it is for you if you want to look at that. Right now, let's say there was a rope, and this is not just a mathematical representation. This is a rope, and it's being, it's somehow there's a machine or a person, and they are oscillating the rope. They're delivering power to the rope, and maybe it's attached somewhere down here to something, and long distance, it's oscillating something else. Well, to oscillate something at a very long distance away from where it's happening, the further away you are from it, the harder it is to transport that energy. There's got to be more, it's going to take more energy to get the job done for something like that to happen. The shorter the rope, the easier it's going to be for me to transfer energy, but I can't transfer it over a long distance. For a long distance, many wavelengths away, and if it's one wavelength away, it might be easy for me to oscillate that rope and do something and move something at the end of the rope. To move something at the end of a very, very long rope, much longer than one wavelength of length of rope, that's much more difficult, okay? To be able to do the same kind of work on that object, you got to put more energy into it. It's going to be more power required in general. So, for our purposes, the way the book, the way Dr. Katz's book talks about it, they don't mention some of that very much, but they mention a lot of great things. So, let's talk about it. Let's say there is one wavelength here, from here to here, and I'm saying I don't know how long the rope is. It could be indefinitely long. I'd like to know how much energy I am putting into one wavelength. If there's two wavelengths, I'm putting in more energy. There's more mass I got to move. Remember, the rope's got mass. Yeah, so what? Well, it's got mass, and you're moving that mass to be able to transfer energy. I mean, there's momentum associated, as Dr. Katz brilliantly tells us in the book. For the 209 people, for the 120 people, I'm sure other people also do great work and tell us, hey, there's momentum, there's energy, what's going on here? Well, waves have the attribute that material is not moving from one place to another, but energy and momentum are. Energy is being transferred from one place to another without the material medium experiencing, it's like the person here is doing the work. This thing right here, the work he's doing is going to find itself over here, but that material doesn't transfer over there. Material is not being transported, energy is being transported. And waves, Dr. Katz tells us that that's a common attribute of waves. Energy gets transported without matter being transported. So, true for all waves, we're being told. All right, if that's the case, well, here's one wavelength. From here to here, and this thing's oscillating back and forth. Up and down rather. It's oscillating up and down this way. So, and we said what happens, right? I mean, well, we know that every single particle on the rope, now again, this is greatly exaggerated and it's sort of, I guess you could say kind of, sort of, you're saying the wavelength is actually the length of the rope as well, or at least close to it. So it's not really mentioned, but it's kind of implied. We're not going to worry a whole lot about that, but I need to say that. Every single particle, this guy too, it's going to go all the way up, it's going to come all the way down. This guy's going to go all the way up, he's going to come all the way down. Yeah, every one of them is. I already said that the last time that we were together. I already said that. That's the case. I mean, as we said, guys, that's the wavelength. Okay, and roughly the length of the rope. What's going on here? Well, every one of these guys oscillates in simple harmonic motion. Didn't we say with simple harmonic oscillators, at one point or another, remember we were talking about springs and stuff, or we're going to talk more about springs, but the energy in any simple harmonic oscillator is equal to the sum of the potential energy with the kinetic energy at any particular point. Wherever you are, the sum of the kinetic energy and potential energy is constant for every single particle on this rope. What does that mean? That means right here, the potential energy plus kinetic energy, the potential energy plus kinetic energy right here is equal to energy E, some energy. And down here, it's the same energy. As it's going through here, it's also that. Well, remember we talked about we said a lot of stuff. The energy of a simple harmonic oscillator, at least the book talks about this too. All the books are going to tell you this basically. When you can imagine a spring. The spring's kind of the standard is how simple harmonic oscillators behave, I guess you could say. It's the easiest one to visualize. But all of these behave, each one of these particles behaves as though it's attached to a spring and it's undergoing simple harmonic motion. It's as simple as that. Remember we said it's 1/2 k x squared plus 1/2 mv squared. The book says that too. I mean, it's like we talk about, and they always add up like this. Well, how do you get yourself out of the woods here? If I know if the thing comes to a dead stop, it's all potential energy. See, it's basically that's all the potential energy, that's all the kinetic energy, and it varies constantly because it depends on where it is. This is like at the very edge of the spring. Hey man, it ain't moving right here. It ain't moving at all. It's all potential energy. Down here, it's all potential energy. All potential energy, no kinetic energy. That's 1/2 kx squared and none of this. Whereas right through the middle, it's like going right through the middle of the spring system. The spring is not stretched, nor is it compressed. Not stretched, not compressed. It's all kinetic energy. Well, I can use one or the other. If I get the maximum, you can basically say that E is going to be KE max, or the E is going to be PE max. Because PE max is equal, all the potential energy will eventually become, all the maximum potential energy will eventually become maximum kinetic energy. So if you find one or the other, you're out of the woods. Well, I'll tell you what, if I can just find, if this thing's if each one of these guys is a simple harmonic oscillator, and it's out, it's eventually going to come down to here, up, down, the whole thing, it's flying everywhere. But here, it's got its maximum. What's going on? Well, it's kind of a weird thing here. I mean, I guess you could say kinetic energy, and different books say different things, guys. So let me try to bridge the gap. Maximum kinetic energy is going to be this guy at its max. Well, this guy at its max is omega of the oscillator, omega of the oscillator times the amplitude. Omega of the oscillator times the amplitude, which is Y max. I've used A in the past when I discussed this stuff. Doesn't really matter. The language can change quite a bit on us. But it's omega Y max. That's omega Y max. Remember the omega A that we talk about. That's the V max. That's equal to omega Y max or omega X max, depending on what you're talking about. Okay? Squared times M times 1/2 is the KE max. Well, the KE max, we just said, was the total energy of the system for one particle, for one little particle. Okay, true. Can we figure this out? Yeah. If one little particle is mass m, I mean, we can say this a whole bunch of ways, guys. We just got to be careful, that's all. Let's say the one little particle is m. If you added all of this particle right here, as it flies through here, that's m. This guy's also m. This guy's also m. Or delta m, or maybe dm is better. Hey, whatever. This becomes a linguistic issue, guys. I tell you what I'm going to do. That's true for one particle. Tell you what. When we look at this, isn't the entire mass, it's the entire mass is m1 plus m2 plus m3. Yeah, I know, but m is equal to any of the m sub n's. You're just going to sum all of these. It's going to be the summation, it's going to be the summation of all these little m's. Yeah, I got a better way to do it. Why don't you get this thing called mu? Mu is the linear mass density. They use lambda in other places, but you can't use lambda here because you got a thing called lambda called the wavelength. So you can't really go there. I'll tell you what I'm going to do. Mu is equal to the entire mass of the rope in one wavelength of length. The entire length of the rope, in general, the entire length of the rope for some length L. Whatever that may be. Anyway, for the whole wavelength, we'll make L equal to lambda. It's that right there. If you take mu, which is the mass of the whole rope per wavelength, and we're assuming the rope is that long, is as long as this wavelength, even though it's curving all over the place here, guys. Okay. Mu is this. The total mass is mu L. And you got omega squared Y max squared. It's almost like the entire mass of the rope is oscillating up and down at once. That's what this is saying. Yeah, it's just like that. Only it's not happening that way, but it's effectively happening that way. Over the course of an entire period, every single one of these guys will have done a whole oscillation. If you start here and go all the way down to there, this guy will oscillate up and down at the end of that period. In the time it takes for that to do it, it'll also have done the same thing right here. Everybody, it's as though somebody just took the rope. It's as though somebody just took the rope, did this, and went up and down all the time simultaneously. Here it's happening, but it's happening over the course of one period. Over the course of one period, this entire oscillation that will take place will find its way over there. Everybody will have done it over that period of time. Period. Done. Then it will happen again over here after another period. Not after one period, 2 periods it'll take for it to come over here. So it does take time to transport it. But in one period, everybody oscillates up and down. Interesting. This is kind of where the 1/2 mv squared comes into play. And that's what they're talking about. And that's the energy associated with one wavelength. Okay, let's try to speak the same language as what Dr. Katz's book says. Those of you not with that book, it's okay. I mean, I'm just reading it to you the way it is for my other class as a non-calculus treatment. For the 209 people, definitely be looking at this as you're looking at it. So you got this. They do a number of things here. They take this. There's nothing wrong with that. That's fine. E sub lambda is 1/2 mu. 1/2 mu omega squared y max squared lambda. They just move the lambda over here. Okay, that's fine. Having done so, they do this. They say, okay, I'd like to find out what the average power is. And I'm just trying to follow relatively closely how they're doing it. Average power is going to be equal to what? Okay, well, let's talk a bit. Let's talk. Okay, you saw me do this. You saw this right here. I just moved the lambda over there. And it got to here. So there's no big deal here. Tell you what I'm going to do. Power average is going to be Let's see what I can say here, guys. Kind of running out of chalk a little bit here. Let me see what I can do. Is going to be, let me give myself a little bit more room here. Isn't work divided by time power? Yeah, that's the period. That's for one whole oscillation to take place. For one whole oscillation to take place, you guys, in the course of time of one big T, as this does all its climbing and stuff like that, it'll create that disturbance. Exactly. That's it. Everybody here, including him, will experience that disturbance in one period of time T. Okay? It's a big thing. You send the pulse, bam, it'll take, in other words, if you're just going to do a pulse, say, okay, let me go all the way up. Or maybe I'll start all the way up. It doesn't matter where you start. But let's say you go all the way up, come all the way down, come back here. Same thing will happen right over there in a period of time T. Now, what is the wavelength divided by the period? That's the speed of the wave in the horizontal direction. And there it is. So lambda divided by capital T, mu omega squared y max squared v sub x. V sub x. And there you go, guys. That's the average power per wavelength. Within one wavelength, what is going on? You know, and that's the big thing. Not easy to visualize necessarily, this whole process, but that's how waves work. If you can, wherever the full oscillation will first be manifested, that distance away from where it first started is the wavelength. How long did it take for it to occur over there where it first happened? That's the period of time, capital T. So it's looking something like this, you guys. They give kind of a similar argument, period. End of the story. That's kind of the basic move being made here. They talk about energy and power of sound. They kind of, let me debate a little bit how I want to do this. How does this whole thing work if you're talking about sound? Well, sound, I'm dealing more with a volume. And let me deal with a box. It's got a cross-sectional area A. It's got a length, lambda. A times lambda is the volume of the box associated with one wavelength of the longitudinal wave called sound. And rho, we'll say, is the mass density of the situation there. So what they're saying, guys, is, let me kind of stay similar to this. We'll say that in this case, small m is the mass of all the mass that's in that box. What's that box all about? The box has a volume, capital V, and there is a mass density, rho, there. Rho is rho, V is cross-sectional area A times lambda. And that's it, guys. It becomes essentially the same dynamic. You look at it, you play the same games I was playing earlier. 1/2 the total mass. The total mass is rho times. This is almost like this is the capital M that I was talking about earlier. I'm just calling it small m now, guys. 1/2 the total mass. 1/2 the total mass, which is 1/2 rho V. Well, rho V is this. Simple as that. And the omega squared times the amplitude squared. They don't use a Y max or an X max here, guys. They use an S. S max is the distance of the oscillation, of the amplitude. They just, the names like that, that's how they write it. They do some other stuff here. They write it in such a way, let me just kind of let me kind of go verbatim with the language I'm seeing here. 1/2 rho A omega squared S max squared lambda. They put the lambda way at the edge. Okay, so it's the same, guys, it's the same monkey business I was doing earlier. You just throw the lambda, you just bring the lambda. Now this is the volume of the box. A lambda was the volume of the box. That was this. So this right here and this right here are the same. And I just move the lambda over there. You know where I'm about to go, guys. If you wanted to find the average power, that's going to be lambda divided by capital T. That's going to be this divided by capital T. Well, what's lambda divided by capital T? Yeah, it's starting to look really familiar, right? P average equals 1/2 rho A omega squared S max squared Vx, the speed of the propagation. It's not the speed of this thing up and down. It's the speed of the propagation going this way. How fast does it propagate? Be careful with that. It's essentially where they're going with that, guys. And that's if you're talking about a sound wave. So there it is for the sound wave. And the other one was for the transverse wave. Look, guys, the mathematics is identical. The argument is essentially identical. You know, the mu is replaced by a rho. The distance, the linear distance associated with the rope is replaced by a volume. Volume replaces the linear distance. Rho replaces the mass density. Volume mass density. Rho replaces the linear mass density mu. So they talk about this, guys. And that's kind of where it's going here. It's some pretty fascinating stuff. I shouldn't have said X right here. It's X, doesn't really matter. They put an S right here, guys. S is the speed of sound in the medium. S is the speed of sound, but it's in the X direction or whatever direction it's going that you're considering. Y direction, X direction, XY direction, whatever direction we're going. Not a whole lot differently here, guys. Perhaps it's no surprise that a dense medium with high wave speed or a wave with large amplitude and high frequency transmits power effectively. If there is a lot of area that we're considering, if there's a lot of area that we're considering, and omega, the angular frequency, which is closely associated with the oscillatory frequency, remember this is what omega is. Two pi over t or 2 pi f, if they're directly proportional to each other. If f is big, omega is going to be big. If omega is big, f is going to be big. If omega is small, f is small, so on and so forth. There's a lot of frequency and a lot of area over which it's going and a lot of speed, and the amplitude's great. All of these point to a tremendous amount of power is needed for that to be accomplished. If that is done, yes, it is conducive to a tremendous amount of power being transported to our ears. or to anything else that it's hitting. You know, it's hitting the walls. It's making the walls, you know, oscillate a little bit or something, okay? So that is the situation. They stay with sound then in this regard, and then they say, okay, well, you get this idea of the decibels and all this other stuff here. I guess a good way to look at it is, guys, in a given circumstance where this stuff is going on, if there's a real loud sound and it's continually going on and I can't really stop it from happening, the next best thing is for me to get far away from it. That doesn't change the power of the sound that's coming forth, but I don't experience it as badly the further I go. The intensity is spread out over a much bigger surface area. Here we go to spheres again. It's like the surface area of a sphere. If I'm close, I'm on the surface area of a sphere that's not that big, so I'm getting a lot of that power head on. It's a very intense experience. The intensity, I, is very great. If I move away, the power hasn't changed, but if I'm so far away, it's as though I'm on a sphere experiencing this thing, which is much bigger. So that's where they get this idea of intensity and how they talk about a lot of this stuff. So let me see where you want to go with it, where we want to go with this thing. And even though, let me just think about, I'm erasing here, guys. Even though one of them is longitudinal, the other one's transverse, I can mathematically describe any kind of disturbances associated with waves like that, even if one of them is longitudinal and the other one's transverse. Mathematically, I can show something like this. That doesn't mean this is physically what's actually happening with a wave that's with a rope that's oscillating up and down. With a pressure wave associated with sound, for example, that pressure wave is longitudinal oscillations. But I can talk about the enormity of the oscillations, the amplitude and stuff like this. I can put it on a graph like this, though physically that's not what's happening. I guess that's what I'm trying to say on that. Intensity is power over area. What does that mean? Well, we'll call it I for intensity. It's power over area. Again, the symbols are repetitive. That looks like pressure also, doesn't it? Well, you run out of letters. So just watch out what we're talking about within the context in which we're talking about it. Intensity equals power over area. And again, I mean, what does that mean? Well, it means a lot of stuff. I mean, for us right here, I could take this power right here. Here's the power. There's the power, guys. And I can divide it by that area, A. So that just disappears, and you got power over area is all of this except for the A being there. That's all. They talk about that. Okay. You can see that. You can see that in the book as well. The area is, since it's going equally in all directions, the sphere is the three-dimensional entity that has equality of representation of how the power is distributed, very well described. It goes everywhere and it hits everything around. You're assuming the power source is somewhere elevated. It's on a tree, it's hanging from a tree, and it's going everywhere, in all directions, equally. As long as they're equal distances away, the intensity is the same. Well, the only way you can have equal distances everywhere the same is a sphere. And there's a whole bunch of concentric spheres that I can use depending how far away I go. I'm on a different concentric sphere if I'm 10 meters away compared to being 1 meter away from the power source, or being 100 meters away to really get away from the power source. It's killing my ears. It's a sphere that's got a radius of 100 meters as opposed to 10 meters, as opposed to 1 meter. Okay. And that's where they're getting this. That's what they're saying, something like that, guys. So it's right here, guys. And that's where the intensity is coming from. All right. They've got a way, there's like a minimum amount, and you know, like I said, power, you guys, is watts, areas square meters. And basically, there's this unitless quantity called the decibel that measures intensity. It's described by beta equals 10 times the logarithm base 10, not base e, logarithm base 10 of the intensity that is being experienced compared to the threshold intensity of hearing, which is I sub 0. The threshold intensity of hearing is 10 times is 1 times 10. The threshold intensity of hearing is 1 times 10 to the negative 11. That's I sub 0. 1 times 10 to the negative 12, rather. 1 times 10 to the negative 12 watts per square meter. And I want to compare that's barely hearing something. I want to compare the intensity that you or I are experiencing at a rock concert compared to the threshold of barely hearing something. And that's where you get the decibel scale. Anywhere from 0 to, you know, wherever it could go theoretically. You know, 100 decibels would be an awful lot, right? But this is where that's coming from. The threshold of hearing, the I sub 0, kind of the measuring stick on that. You know, so we got this. And that's where the I sub 0 was that I just talked to you guys about. Okay, so some of what they're saying there, guys, I guess you could say. There are some other things. Just trying to go into. It's hard to know what would be a good order in which to do some of these. I mean, I want to do all of them. I intend to do all of them. So we're not going to worry too much about how we're going to do all of them. We're just going to simply do it while we're at it. And there we are. Okay. Now, I'm about to tell you about this thing called refraction. How a sound wave can be bent. Or how any sort of wave can be bent, I guess you could say. They're talking about, you know, let me just see here exactly, guys. Let me just say something. In general, what happens with waves, we can say this arguably for any kind, even a wave that would take place, let's say, with an earthquake, or there's sound propagation, and it goes from air to water. Can people hear it? What happens? How does it get bent? Well, waves get, and then you see this in light waves too. When you get into optics, you're going to remember this law of refraction. It holds universally for a wide variety, if not all waves. I mean, they're not really saying here. It's kind of just out there, I guess you could say. The musician 1, musician 2, certainly for sound waves, certainly for light waves as well, would also happen with an earthquake. I could see no reason why it would not happen that way as well. If it's going from two different mediums, there's going to be a bending of the wave. Well, how does that work? Is there any kind of like gut feeling look we can have on this, the law of refraction? This will especially take a significant value when you talk about light waves, because it does happen quite a bit there. Well, let's try to give some kind of a gut feeling for what might be happening here, guys. Let me do a couple things here. Okay, guys. I am going to see exactly what I'd like to do here for this one. Now we're saying, I mean, like I said, I'll go kind of verbatim here on this, guys. They talk about, the way they have it in this volume of the book, I guess, before we get into electricity and magnetism, which is not our business for 209. That's more of a 210 thing. They talk about how musicians are experiencing stuff. So it's associated with sounds. For our purposes, we will say, we work under the assumption this is we know it's possible for light waves, and for sound as well, because we're bringing it up in this section. But I think generally this is going to be the case. Waves behave in this manner if they're going to go for if how they propagate has some association with the medium in which they're in, and propagation speeds change because of the medium in which they're in. If the propagation speeds change, there will definitely be refraction. There will definitely be a bending of light when that happens. If the mediums play a role in the speeds, and they are different across mediums, there's going to be refraction. Whether we're talking about sound, or whether we're talking about light, or whether we're talking about, I'd assume even an earthquake as well. I think that the mediums are kind of the big thing here. Why do we argue that that's the case? Why do we know it's the case for really the very significant phenomenon such as light, and for sound as well? How do we know that? Well, let's kind of take a look try to see what I can say here, guys. This is a boundary, and there's no reason this should not apply to all waves if there is dependence upon the medium regarding speed. Because if I get slowed down if I'm transporting something very big and it's long this way and I'm going very well in one medium, and then I all of a sudden hit another medium, only part of the object initially hits the other medium, and that medium slows it down, then the other side of the object is still going to be going fast, and its direction has gotten changed. There's been refraction. So that's the argument here. So let's look at it. Well, I'm going to say that, just want to argue this point, I guess. This right here, this length right here, that length right here is the hypotenuse. That's h for hypotenuse of a triangle. And let's kind of look at the ray, the angle. I'm going to try, again, we're talking about a few things here. Let's just make sure it's going to go well for us. Just want to make sure the drawing's going to be good. There's a wavefront right here, guys. There's a wavefront right here. coming in at theta 1 at this boundary. I just said it depends on the medium. If there is no difference in the medium, in the mediums or media or whatever you want to call them, right? If medium 1 and medium 2 are exactly identical, then there's no point calling them media 1 and media 2. It's one medium, and there's going to be no bending, no refraction of the wave. If the two mediums are different and they cause the speed to be something different, one different from the other, depending upon the medium is in, there's going to be that bend. There's going to be that refraction. So here's this wave coming in this way, straight on that way. And just trying to, I want to make sure when I draw this stuff, guys, it's not going to be too bad for you guys. So it's coming in like that. Try to think how I want to do this. This guy's already gotten to the place. This medium right here looks like this. It's different . So you got that. I think you guys can see the difference. You got this, and that's different from this guy. This is a different medium. You have two different mediums. What do you mean? I mean, this guy's medium 1, and he's different from medium 2. There's medium 1, there's medium 2. Interesting. Yeah, okay. It's not, I'm just trying to argue. I want to draw this as nicely as I can. Let me bring it to here. The explanation's pretty easy, guys. It's the drawing's kind of from another planet sometimes. All right, so we got that. That's a 90. So it's going to hit. It's going to hit at a 90-degree angle, and it's coming out. It's coming here. So. And so let's lengthen that hypotenuse a little bit, guys. Here's the hypotenuse. Okay. And there it goes. It's going. And I want to talk to you. I mean, this guy, here's the wavefront. It's moving it's moving perpendicular to the front. The wavefront is perpendicular to its direction of motion. That right there is perpendicular to this, and bam, it's flying this way. This guy just hit medium 2. Something's going to happen. This line, right, this white line right here, this part of the white line just hit medium 2, and it's going to get slowed down. This guy's going to keep going fast, though, until he comes over here. After all that happens, this one right here, let me see here. This guy right here is going to be Guys, I just want to be extremely careful when I'm doing this. I just want to, like I said, I could easily not do what I'm about to do, but I think it's maybe a good idea to do what I'm about to do. Well, yeah, something happened here. I mean, it hit, and it kind of got knocked off a little bit. It was going this way. It was going this way, and it got slowed down. This guy's still going fast. He hits right here, and the wavefront, it hits right here, but this guy, during the time t that this guy was moving over here, this guy did something. Let's say he did this. I mean, in that same time t, he got that far. So what we have here is you got the original wavefront here, and you got the wavefront at the end of this thing. Try to make it went here. And that's 90 degrees. Okay, what's going on? What's going on here? Well, this guy is here. This guy is here. And what has gone on here? Well, I can see there's an angle here that's kind of... Okay, there's an angle here. What's going on here, guys? Well, I'll tell you what's going on here. If this is 90 degrees and this is theta 1, this is 90 minus theta 1. And the whole thing, this whole entire thing is 90. This whole entire thing is 90. This is 90, this is theta 1, this is 90 minus theta 1. This is also theta 1. Same as that guy. All right. This angle got bent. This way, now the wavefront's doing this, guys. Now the wavefront is moving like this. So he got knocked off course compared to how he was going initially. And this is theta sub 2. That's theta sub 2. And if this is 90, and that's theta sub 2, this is 90 minus theta sub 2. The whole thing is 90. So this is theta sub 2 again. Okay. Well, all right. I guess here's how I got knocked off course. I mean, it got, the way these guys are moving, where they're hitting, they're hitting in a lot of different ways here. I mean, what's going on is essentially, again, the way I want to describe this, if you were looking at it, I almost don't want to say this, but I will. If this is going to be theta 1, looking like, if this was theta 1, then this guy is theta 2. Basically, you could take this angle, you could take this reality, this angle, and move it over to this side. And about the vertical, there's theta 2, there's theta 1. That's kind of how you look at it, especially when you get into light, they start using language like that. That kind of look to it. Believe it or not, if this guy is theta 1 right here, if you brought this guy, I'm not going to do it because I just think it might be more confusing than helpful. You take theta 2, pick it up, slide him over here, slide him to this side, and it's always this. It's always as we said, it's here's theta 1, here's theta 2, and notice right about the vertical is where you're talking about these guys, how they go. And that's really what's happening here in a backhanded way. I'm not telling you explicitly until now, and now you know now you see it. A lot of times you can argue it that way, you don't really need to say it, but that's really what's happening. Okay. Here's how they're moving. Moving this way. Man, it's a lot different than moving that way. Yeah, these guys made it happen. You know, here's medium 1, here's medium 2, and that made the whole thing happen. This hypotenuse is h. It's the same length for both, and both of these are right triangles. I got a question for you. All of this happened in a time t. Small t, capital T, whatever you want to call it. We'll call it small t. That's one we're used to, because nothing really in particular is going on with oscillatory motion right now, at least explicitly talked about. In a time period small t, what happened? Well, this wavefront was moving, and in a time period small t, this wavefront was moving, and part of the wavefront collided right here with medium 2. It was moving in medium 1, and it collided with medium 2 right here. This part of the wavefront did not. It kept going, and then it collides right here. By the time it collides right here, this guy already moved a little bit, but not as far as he used to. Why is that? Because one of them is moving faster than the other. Who's moving faster? Look at the triangles. What's longer? This guy right here, this whole thing right here is D1, which is V1 times T. This guy right here is D2, which is V2 times 3. I told you there's going to be different speeds of propagation depending on the medium. Okay, what does that mean? Well, I guess the hypotenuse is h. It's the same for both. Let's do some trigonometry. The sine of theta 1 is d1 over h. Is d1 over h. The sine of, and let's see how they, it doesn't matter, guys. We'll straighten this out later. It's not, the big thing is the big picture, I guess. The sine of theta 1 is d1 over h. The sine of theta 2 is d2 over h. True. Absolutely true. Now what? The rest is pretty easy. Sine of theta 2 over sine of theta 1 equals d2 over h divided by d1 over h. Wait a minute. Fraction divided by another fraction is the first fraction left alone, multiplied by the reciprocal of the second fraction doing the dividing. True. What's that? It's V2 times t. What's that one? It's V1 times t. You're looking at it. And that's where we can do a lot of work here. Let's just see. Let's see what we got here. Sine theta 2, sine theta 1, Yeah, that's what they're talking about for the law of refraction. That works for light. It works for everything. Everything to where it applies. It definitely applies to sound. It absolutely applies to light. You're going to see it again with light. When they do it with light, they're going to put this thing called an index of refraction. There's going to be an N1 and N2. Well, that's a bridge we cross some other time. But essentially, it's derived like this. It's going to have a different look to it when they talk about it with light. But that's all. And I got that in the notes. When I talk about the law of refraction, you guys, I have that for you. I think that might be of, I think that'll be of use to you. Either way. So, okay. There are a lot of things here, guys. A lot of things can be said, I guess you could say. I do have, I think I've already mentioned this, but I'll mention it again, and I'll do some problems on it as well when it's time to actually do so. There's this thing called the Doppler effect, if you're going to talk about sound. Now, this works for sound. Definitely works for light. It works for waves in general, where the media are different and they result in different wave speeds of propagation. The propagation of the wave speed is going to change because of the medium. We're talking about refraction. Okay. Let's keep talking, I guess. There is talk about the Doppler, and like I said, I'm going to get into problems on these, you guys. I'm going to do problems regarding this stuff, and so wherever it applies, guys. I mean, you never say never, never say always, but there's very broad applications of this when you're talking about refraction and talking about a lot of other stuff. And the mathematics so frequently manifests itself in so many places, so many diverse places when you're doing all of this. So let's see what we can say. Okay, guys. The Doppler effect basically says, and I've got a proof. I've got my own version of a proof of the Doppler effect. I'm sure I'm not the first one to have proven things in this manner. It's probably very similar to what books do. I just couldn't really follow the way they were doing it, so I kind of did it my way. So it's probably very, very similar to what they're doing. I'm just putting it in other words. I wouldn't doubt that. But again, everybody's got to make things make sense to themselves. I have an example. I have a proof of that for you guys. I think you might find it of interest. You don't have to know it, but you want to know how to use the Doppler effect, whether you do my proof or not, or some other proof. Be able to apply it, have a gut feeling for what's going on here, guys. They talk about this thing called the Doppler effect, and basically, if there are, just to write something maybe, if there is motion going on, you are going to experience a frequency of sound. If you as the observer, O for observer, and the source, S for source, if my speed relative to the source, the observer, me, my speed relative to the source is 0, and the source's speed, or relative to the ground, my speed is 0, and relative to the ground, the source's speed is 0. If we're both not moving and the source is 100 meters away from me, I'm experiencing the frequency of the sound that the source is putting forth sound, and I'm experiencing the frequency of that sound in a particular way. I'm experiencing the frequency of the source, period. If the source starts moving away from me and I'm standing still, I'm going to experience a different frequency. It's not going to be F sub S, the frequency of the source. It's going to be F sub O, the frequency I observe. the frequency I observe and the frequency of the source, the frequency that I observe and the frequency of the source are equal if none of us are moving. Okay. So there's other ways where this could happen as well if there is motion. We can kind of talk about that. If I was, let's say, if the source, for example, if the source was moving toward me and I was running away from the source, if I'm running away from the source, and the source, well, let me see here exactly how we would actually. Let me talk about the hypotheticals a little bit later, guys. Here's one hypothetical that we can all agree on. If nobody's moving, the frequency I observe is the frequency of the source. The frequency I hear, the frequency my instrumentation picks up on, the frequency my instrumentation picks up on, the frequency that is observed is the same as the frequency of the source if nobody's moving. If the source moves away very quickly, there's going to be a change in what I observe. If the source moves toward me, I'm going to be experiencing a change in. I'm going to think the frequency I observe is different from what the source is. Same thing if I run away or I run toward it, etc. Any combination thereof likely to be different. But if they're both standing still, you get this right here. Well, there's a number of things you can say, guys. They've got this, let me see where I'm going to write this. FO equals frequency observed. FS equals frequency of source. Different books write different things, you guys. This is the way I kind of always describe it. The books do different things in different places, and sometimes even within the same book, they modify what they've said, and they write it in a little different manner. The way I've seen this stuff expressed, I think this is probably the easiest way to look at it, what I'm saying here. I think you're going to see what I'm talking about. As I said, I do have a proof of this. I'm sure I'm not the first guy to have done the proof like that, but like I said, it's there for you if you want it. It's on canvas. V is the speed of sound. VO is the speed of observer. Vs equals speed of source. Yeah, let's leave everything as positive numbers. They do different things in different books, you guys. As I said, the literature has a number of ways this gets looked at. Not a big deal. Just know this much. If everybody's positive, just get an idea what you're going to add or what you're going to subtract. This is all easier done than said. The frequency observed is equal to the frequency of the source. What you will observe with your instrumentation or with your ears, the frequency of sound that you will observe is equal to the frequency of the source, if it were stationary, times the following ratio. The speed of sound in the particular medium, and we already just been discussing that with refraction. Mediums have different speeds depending where you are. The speed of sound in steel is not the same as the speed of sound in air, and is not the same as the speed of sound in water. The speed of sound in water and the speed of sound in air are two different dynamics, as is the speed of sound in steel, for example. This is odd, but easy at the same time. What's going on here? That's the speed of sound in a particular medium. We're saying the mediums aren't changing on us. They did change on us when we talked about refraction, but they're not changing now. The speed of sound in the particular medium under consideration, plus or minus the speed of the observer, divided by the speed of sound in the particular medium under consideration, the same medium as it was here, minus plus the speed of the source. What is going on here? What's going on is this. I'll tell you, you will run head-on into sound waves. You will run head-on into sound waves if you are running head-on into the source. And if the source is running head-on into you, you're running at the source is running at you, the sound waves kind of get bunched up in a sense relative to you. In other words, you are experiencing the frequency of the waves are hitting you. The waves are hitting you more frequently if you're running at the source, and if the source is running at you, they're doubly hitting you more frequently because it's running at you. So that's a situation where you're going to have the most observed, the biggest number for the observed frequency. What does that mean? That means if I'm the observer and I am running toward, if I'm running toward the source, then it's V plus VO. I'm running toward it. And if the source is running at me, they put a minus there. If you look at my proof, you'll see why there's a minus there. I mean, if you look at any book's proof, you'll see why there's a minus there. I'm partial to the way I looked at it, but then again, it's got to make sense to me. What makes sense to me might not make the most sense to you. Maybe the way the book does it makes a lot more sense. So whatever, that's your business. I have that for you, though. Basically, if the denominator is a small number and the numerator is a big number, big divided by small is huge. This is the scenario, ladies and gentlemen, where you're running right at it and it's running right at you. If you're going right at it, it's a plus. You're the observer. Your speed plus. If it's running right at you, it's speed minus because you want a small denominator to get a big answer. That's if they're both running at you. That's if you're both running at each other. If, let's say if you are running away, you're running away from it, that's minus, but it's still running at you. If its speed and your speed are equal, V minus VO, and VO is the same as VS, V minus VO divided by V minus VO, that's 1. Fs equals FO, etc., etc. If it's running away from you, and you're running away from it, wow, that's really small. It's running away, that's a big number on the bottom. You running away, that's a small number on top. Small divided by big is tiny. Yeah, I'm running away and it's running away. Yeah, I'm not really here. The frequency is not, the waves are not hitting me very frequently. So on and so forth. If you are running at it and it's running away from you, and let's say VO and VS were equal, you'd still be hearing it the same way. That's what I was trying to say earlier. I wasn't really comfortable until I wrote it down. But anyway, so on and so forth, guys. That's how this is playing. That's how this whole thing plays out. When you see me do some of the problems, I think you'll like them. I think you'll find them of interest. They're like kind of like there's some of them are like those classic GRE type problems or SAT type problems. You can kind of still it's what's really appealing. The mathematics is not particularly difficult, but it will make you think, and it can be a real challenge. That's a neat thing in its own right. Okay, so that's where we're getting the Doppler effect. And again, more to come on that when we do some of the problems related to it. There is Guys, I'm like summarizing, 3 chapters here. That's why it's kind of a little bit of a mess sometimes. There are these things called standing waves. And there's a whole bunch of other stuff in here as well, guys. But you guys are going to read it. We can add 2 waves together and get. I've kind of been talking about that. I've already kind of mentioned the Fourier Series, and which is really just an addition of a whole bunch of different waves together to get some big master wave, or get some wave that has all these periodic characteristics, but man, it looks really odd to look at. How did you get it? Well, I added all these simpler waves together and I got this more complicated wave. And I can describe practically any periodic function that I want by adding simpler waves together in a particular way. I may have to do it an infinite amount of times, but in the limit, I can get any wave to look. I can construct any wave from the addition of simpler waves. And that's where the Fourier series comes in. I talk about that a little bit in Canvas. And again, Sokolnikov handles it better than I ever could, and than most other people probably could do as well in his book Advanced Calculus from 1939. Okay. So let's talk. Let's talk a little bit about that. They are saying, guys, that if you're going to talk about a wave, and we talked about traveling waves, right? We said the wave travels. Yeah, it does travel. What if it doesn't travel? What if could you kind of make it stand in one place? Could you somehow add 2 waves together and make it so that they stand in one place? Yeah, I think you can. Let's see. The mathematics runs the show. If the mathematics, that's what I've been saying earlier, guys, when we're talking about refraction. The mathematics can tell us a lot, whether it's a hypothetical reality that we're discussing, some sort of hypothetical mathematical situation, or even a physical phenomenon that we're observing. Can the mathematics describe a lot? Yes, absolutely it can. So let's see. Well, I'm going to give you a real basic look on this thing, and then we'll just kind of call it at that. And I think the problems will manifest themselves. This should be good. It should help it should help you out, I think, a good amount. Give you a gut feeling for some what's going on. I'm hoping that's always the goal as we proceed with this stuff. Well, I just said you can add 2 things. You can superimpose 2 waves onto one another. Superposition. I just add the 2 together, and I get a new wave, right? Okay. Well, I've been saying that. I've been pointing to the brilliant work of Red Heifer and Sokolnikov, and just Sokolnikov by himself as well. Some of the brilliant things that were said there. So I've been talking about that, and absolutely, it's definitely true. So let's see what we can say here, guys. Is it possible for the wave not to be traveling? Is it possible for it to just be oscillating up and down and not traveling? Not traveling either. Not traveling to your right. Nor not traveling to your right, nor is it traveling to your left. It's just standing still. Not standing still, it's oscillating up. There's all kinds of oscillations going on, but there's no energy being transported further away than particular limits where we are. It's in some particular place. Could that happen? Sure. There are waves that can happen in the ocean or in a harbor or something where there's the reflection of waves in such a way, waves are hitting someplace, they're bouncing back, and they're interacting with one another, and it just looks like the waves are going up and down and not going any further. So it's a superposition of 2 waves, or something like that can happen. Well, I'll tell you what, let's kind of, there's always a number of ways this can be looked at, but let me try to make it, I think, reasonable. Let's say I already mentioned this, one of these equations earlier, and all of them are born, they're all born from this, or can be born from this, can be derived from this. We talk about some of the beautiful mathematics, or at least I mentioned it without great detail on it, some of the beautiful mathematics associated with that, and how you can always do a whole lot of things with it. Well, I'll tell you what, there's a lot we can do. If you manipulate it right, there's a tremendous amount that we can do. Let's talk about some results that can happen. I've already talked to you about this particular entity, sine alpha plus sine beta, let's say you were adding two different sine functions, or it's the same sine function, but just the argument in here, maybe there's a different argument. The alpha and the beta are two different things. Well, if you do this, using this in a very rigorous fashion, you can derive all of these things. Not necessarily easy, but it can be done. Using this mathematical reality, we can derive many things, including what I'm writing right now. Okay, it's pretty kind of out there. It's kind of similar to what was going on with the Doppler effect. You got the plus minus, minus plus. Once you pick, for example, ladies and gentlemen, once you pick the top scenario, you're dealing with the tops. So what does that mean? So let's pick. I mean, like if you pick the minus, the bottom scenario holds. If you pick the plus, the top scenario holds. So let's see what we can say here, guys. Let's use the plus. Alpha and beta, that's debatable what you want to do on that, but let's deal with it. This is the plus. So many ways to go here, guys, but it's not our concern. We're going to go relatively easy on this. There you go. Got that. Sorry about that. Didn't have that on there. Okay. So if you do that, and if you were to take now say, okay, tell you what, let's do two standing waves. Let's take two waves. One of them, the argument alpha, the thing that's in the argument right here, alpha is kx minus omega t. Beta is kx plus omega t. What's going on here? These two things are identical except for an addition symbol in one place and a subtraction symbol in the other place. These two waves, ladies and gentlemen, are identical in every way, shape, and form except that one's going to the right, the one that's got this is going to the right, and one's going to the left. Otherwise, they're identical. They collide, they superimpose, and they do this standing wave where there's no propagation left or right. They're just oscillating up and down in a particular way. And that's where we're going to get into these things, the harmonics that we're talking about. So you got this. You got that. Let's see how let's argue how we're going to do this. Try to save a little bit of time on it, but I mean, you guys have the background. Let's just see what we can do. Let's just do this in our heads a little bit. If we need to go further, I'm not feeling comfortable with it, we'll be a little more rigorous about it. But let's see what we got here. I just said this guy, anybody associated with him is going to the right. Anybody associated with him is going to the left. And they superimpose on each other like that. A wave the waves are hitting a place in a harbor and it's reflecting off and they're just doing standing waves. I'm looking at one part of the harbor, the waves are just going up and down and nobody's moving. Well, really the wave is really going this way and one's really going that way. But in certain areas, I guess you could say, in a certain place, it's just going up and down as a result of those two waves hitting each other. Well, here they are. Here are two waves. They're hitting each other. Is that even true? Well, I just said, through the beautiful mathematics associated with complex analysis and associated with the exponential function, base E, And what arises from it, e to the I theta equals cosine theta plus I sine theta, is it true? Okay, well, I got this. That's here. Come over here. What is alpha plus beta? This is alpha. Okay. That's alpha, and that's beta. And okay, alpha plus beta. Kx and Kx is 2Kx. Okay. Negative omega t and positive omega t is 0. So, in this instance, as I added sine Kx minus omega t plus sine Kx plus omega t, there you go, I did it right here. Sine Kx minus omega t, sine Kx plus omega t. As I did this, I got alpha and beta, Kx and Kx is 2Kx, negative omega t and positive omega t, 0, 2Kx, so it's sine, it's 2 sine, yeah, it's all good either way, no matter how I say this. Sine 2Kx. Interesting. Okay, that's the first situation. And the other one is cosine a half times alpha minus beta. Alpha minus beta. Here's alpha. Here's beta. Kx, alpha minus beta. Kx minus Kx is 0. Negative omega t minus omega t is negative 2 omega t. This is rather interesting. You'll see what I mean in a second. 2 is 2. You can't bring that into the sine function. The sine function's here. Half of 2Kx is Kx. Full stop. I don't see any time in this term right here. Half of negative 2 omega t the cosine of negative theta is the same as the cosine of positive theta. You can just as easily write it like this. It was negative omega t, but cosine of negative something is the same as cosine of positive something. This is interesting. They ain't moving. For any particular x that you're talking about, if you pick an x, any x, let's say it's between, and again, I'm going to do this a little differently some other point, but pick an x here. Here's x equals 0. Here's x equals pi. Here's x equals negative pi. You pick any x you want. Once you pick that x, you're locked into a value. You get y. At the end, you'll get y. You pick an x, you're done. You're here. You just picked an x. 2 times this guy, 2 times the sine of kx is something. Yeah, let's pretend the cosine is at its biggest place, 1. You got the biggest place it can be, which is right here. Or, you know, if it's a negative 1, it'd be right here. But as time progresses, cosine omega t oscillates between -1 and +1. So this guy will oscillate up and down right here. Go to another x, whatever it may happen to be. And I'm not picking good numbers here. I want the sine to be the biggest value it can be on this one. So it'd be something like, what I'm about to show is not much different, guys. But let me just show it differently. 0 and 2 pi, let's say. Okay, so we'll go here to pi. 2 pi. We can do a whole bunch of stuff here, guys. Let me not label this too. Let me not label the points. Let me just say this much. There is a place where this guy, if the cosine of omega t is 1, this sine kx can be anywhere from here, let's just say from here, this is the biggest, let's say that's the biggest place, pi over 2. This is pi down here. It could be like this. And the bottom part, basically what I'm trying to say, guys, I could get, let's somehow figure out, you know, I don't know what k is, it's get a little confusing. Let's worry about kx, and let's find the sine of kx. Well, let's start at 0. The sine of 0 is 0. The sine of pi, so the sine of 0 is 0. It doesn't go up. It's right here. Sine of 0 is 0. Sine of pi is also 0. Sine of pi over 2 is 1. Okay, good. And sine of something else is up here. And sine of something else similar to that is over here. And, okay, great. Pick any one of these. Let's say you found this guy. It's 1. Sine is 1. Multiply by 2. This is too high. Then, pass the time, ladies and gentlemen. The cosine is going to oscillate. The cosine omega t is going to oscillate between -1 and +1. It's going to make this guy jump up and down. It's going to make this guy jump up and down. It's also going to make this guy jump up and down. And that guy jump up and down. How about this one? Yeah. But he ain't going to get bigger than where he is right here. He's not getting bigger. He's not getting smaller. Not getting bigger than this. Not getting bigger than, but he's going to oscillate about this point. And every single x value you got, there's a sine function that'll vary. There's a lot of ways it would vary, I guess you could say. There's a sine function that would vary between 0 and 1. If you're talking about between 0 and pi. When you're talking about between 0 and 2 pi, it's going to be from -1 to +1. But once you lock into it, you're done. This guy, you're done. You got it here. And this guy just makes it oscillate up and down. This is a standing wave. This is a standing wave. The result of it is this guy. And that's how they come out. If you add them the right way, you get the standing wave that we're talking about. Well, there's some interesting standing waves that give us these things called the harmonics. And what's that all about? So let me take a quick look at that, if I could. Okay. Well, it's not too bad, guys. This should go okay. The book's, got good coverage of it as well. Let me just kind of give you a gut feeling for what's going on with some of these harmonics and what we can do about it. If you had, I already kind of did it, sort of, right? There's two places here. The string is tied, and you pluck the string and it goes here, bam, and then it reflects and comes right back here. And it oscillates up and down, like that. There's another string, same length. Let's say this thing right here, this length right here is capital L. I pluck the string and notice when I pluck the string, this guy does not get any taller nor any lower than where it is. It's everywhere to be found, everywhere here. This guy's not going to be anywhere. It's going to oscillate between here. It's going to oscillate between here. And it's just reflecting, continuously reflecting back and forth. There's your standing wave. And it's consistent with the mathematics that I just did. All right. Well, okay, that's good. That's fine. What about this? What about one where this would happen? And then bam, it reflects and comes back this way. That's a little different. Still doing this. Okay. What about same distance now? L between them. This describes a lot of stuff, guys. Well, how about this guy? Well, this is, I want you to look at it carefully now. I just put a line through it. That's one hill. This is two hills. Let's do three hills. And it's going to be three hills now for that guy, and it's doing this. I think you get the picture. Let me do one more, and I think you got the idea. Same distance between them. I don't know how well I drew this. I mean, one looks larger than the other as far as like how far apart they are. It's about right. It's a little too much, but not a big deal. Not a big deal. Four of them, huh? 1, 2, 3, 4. Okay, you got this. It's four of them. Up and down. You get the picture here. What do we got? We got one hill. We got one hill, two hills, three hills, four hills. We can go 5 hills. N is the number. Okay, N is 1. N equals 1 right here. N equals 2 right here. N equals 3 right here. N equals 4 right here. So far, so good. I'm just checking, make sure the stuff looks okay, guys. I want to make sure you look okay. We're doing this okay. All right. Well, okay. I got to tell you something. These are examples of the harmonics. This is the first harmonic. This is the second harmonic. This is the third harmonic. This is the fourth harmonic. They arise from the sine function or the cosine function. Sine n theta. Sine of theta, or sine of 1 times theta, sine 2 theta, sine 3 theta, sine 4 theta. You think, what are you talking about? What's up there? This does normal, I mean, it's a little on the odd side now. This thing goes this way, bam, reflects and comes back that way. The whole wavelength is there and back. You want the thing to look like this. But if you cut it here, this guy right here is really right there. The wavelength is L and L. Lambda equals 2L for the big guy, right there, for the big one. So this oscillates faster, twice as fast. This oscillates twice as fast as that. This oscillates 3 times as fast as that. It'll do a whole cycle. The guy in the 3, he'll do a whole cycle at 2/3 L. This is L. He'll go 2/3 of the way across and do a whole cycle. 2/3. So 2/3 of the way across. 1, 2, 3, equal of them. There's 2 here, mountain and low mountain, mountain and low mountain, whole cycle. 2/3 L is the wavelength. Yeah, here the wavelength is L and L, it's 2L. How does 2L compare to 2/3 L? Put the equals right here. I'm running out of room. The L's cancel. The ratio is 3 to 1. This guy's wavelength is 3 times longer than that guy's wavelength, etc., etc. This guy's wavelength is 1/4 as long as the long wavelength, or the wavelength here is 4 times longer than this guy's wavelength. Yeah, I know, but they still propagate. They still move. And they move at the same speed. So if I have less of a wavelength, the period, if I have 1/4 the wavelength as the long one here, if we go here, if this is 1/4 the wavelength of the long one, and I still want it to be the same speed, its period has to be 1/4 the period as the long one's period, which means 1/4 the period means 4 times the frequency. Short wavelength means greater frequency of oscillation up and down. How much more? 1/4 the wavelength, 4 times the frequency that this guy has. And that's where they're bringing, that's a lot of what's happening when you do something like this. So, and they're coming from these. These are called the harmonics. And with the Fourier series, as Dr. Sokolnikov had brilliantly said a long time ago, and other people have brilliantly said it, much better than I could ever say it. Combinations of these, you can basically construct any periodic function that you wish. So, what's going on? Well, we know, I told you they all go in the same speed now. V equals lambda times F as a general rule. And V equals lambda sub n times F sub n for it to work out. So what does that mean? It means a lot. We said from here is half a wavelength and bam, the reflect. If you really want the whole wavelength, you'd want the guy to be coming out over here. Hey, from here to here. Okay, yeah, I got it right here. It's so long, it's got to come back onto himself. But that's the whole thing. That's L and L. So what's going on here? Lambda sub n is equal to 2L divided by n. Yeah, I know, n is 1 right here. N is 1 right here. F sub n is, well, I mean, you tell me. F sub n would be, V divided by lambda sub n, which would be V divided by lambda sub n. And what's that? That's 2L over n. Okay? 2L over n. V divided by 2L over n is, let me just see how they write. I want to just agree. There's nothing wrong here. This is fine. Just want to make sure I'm agreeing with, use their notation. I'm not crazy about the way some things get mentioned, though, to be honest with you. Yeah, okay. All right, I can buy that. I can buy into that. And V over 2L, yeah. So what happens here is, what is that? V over 2L divided by n. The n flips, the 2L over n flips, and it's n times V over 2L. So n times V over 2L for F sub n. And here, 2L over n how long is the wavelength? It depends on what harmonic you're talking about. The bigger the number of hills that I talked about, right? The number of hills tells you the number of the harmonic. And that's the number that's going to be inside the sine function. Sine n theta. N is, that's where it's going. Or cosine n theta. It's either one, because cosine and sine are very close together. Lambda sub n is 2L over n. 2L is the wavelength of the first harmonic. And then, so that's a 1. 2L, what's 2L divided by 1? Oh, 2L. That's what I said. 2L was the wavelength of this guy. What's the wavelength of the other guy? It's L. Et cetera, et cetera. What is the wavelength here? The wavelength of this guy is L. Wavelength of this guy, the wavelength of this guy is 2L. Wavelength of this guy is just L. So this is 2L divided by 1. That's 2L. This is 2L divided by 2, which is L. This is 2L divided by 3, which is 2/3 L. And this is 2L divided by 4, which is L over 2. Yeah, that's right. Right here, that is half a wavelength. Lambda sub 4 right here really is L over 2. That's 2L, because that's where it came from. It came from 2L divided by 4, et cetera, ladies and gentlemen. So this is where it's coming from. All of these, for the same exact separation, for the same exact string, same exact temperature, same exact everything. When you pluck that string and you're trying to get this thing to go, or however you're setting up these standing waves, the speed of propagation is the same. Therefore, a long wavelength does not require a big frequency. True. A short wavelength does require a big frequency. The frequency is going to be big. Why is that? Because V over 2L is a constant. V over 2L is a constant. If you multiply by n, and n happens to be a big number n means big frequency. Right. Big frequency, though, if n's a big number, 2L divided by n is small wavelength. When you multiply the two, you are going to get that. You're going to get the same thing every time. Why is that? Well, if you look, okay, sorry guys, my chalk is all over the place here. I'm making the claim that it's always going to be this. I'll sort of prove it to you in the sense that we constructed it that it would work. That it would indeed work. Let's actually, is that true? Well, let me see. The only variable is the n, and that flies out of there. This is 2L over n. That's 2L over n. The other one is n. Okay. Sounds good to me. N and n cancel. Yeah? I got more than that. 2L and 2L cancel. Yeah, every time it's going to be that way. You saw me. N was not a specific number. It was a general number in the harmonic sequence, so to speak. N could be 1, 2, 3, 4, all the way to infinity. You know, at least for the mathematics here, you guys. So we got this. So this is what they're talking about regarding this stuff. This is what I want to say. I'll do more. I'll do problems when, you know, as soon as we can. We'll get to it. There's obviously a lot more here, guys. And any book you're looking at, make sure you're looking at the whole book. I'm showing you as many of the problems as I can to look at this stuff. Canvas is going to have a lot more of the problems than I'm able to do on film. On film, it's a little more difficult to do this stuff. Just the logistics of it and stuff. But they've been great having us here, and so it's working out great for us. I thank you guys very much. We'll talk soon.